Separate.
عاوتاني جبت السين.
Separate.
عاوتاني جبت السين.
Hello everyone. How's everyone doing? Hopefully everyone's doing great today and excited for our part 2 of satellite image segmentation. So just as a quick poll, who on the stream was here yesterday as well for part 1 of satellite image segmentation? Just a quick poll in the comments. If you were, let me know. If not, that's totally fine. We will actually not be starting from, or we will not be picking up where we left off. We will be starting from, I would say from scratch, but we will be using some of the ideas that we learned from part 1 that will be very relevant to part 2. But again, if you weren't here for part 1, not to worry. We are going to be starting from, or if you are a beginner or new to this, that is completely fine. You will not need to know anything from beforehand. So that is great. So again, just put in the comments if you were here yesterday. If you weren't, again, that's totally fine. Just want to get a quick idea of how many people were here. If not, again, no worries. And again, if you haven't already, please do make sure you check in to the event. I did send the link earlier. You can also find it in the Discord. All right. So we went over a little bit about image segmentation for satellite images yesterday, and we really touched on the pre-processing part of it. So a lot of it was just based on, okay, what actually goes into pre-processing images before they are ready to be, before we're ready to run any sort of AI or ML algorithms on them. So that's really what we're going to be working on today, is using an AI or ML algorithm to actually, make it work, right? That's something that's important. We want to see sort of what the other side of it looks like. We did check out the segmentation and everything as well, but it's useful to see how everything looks in the background. So that is what we're going to be doing today. Let me set a few things up. So again, today, so let's see, we did have a question from Moose's. If this is a part 2 stream, yes, it technically is a part 2 stream, but you didn't have to be at part 1 in order to know what's going on at part 2. We'll be starting part 2 as if it's completely from scratch. So don't worry if you weren't at part 1. we are going to today actually be building a image segmentation model itself. And we'll be doing that using PyTorch in Google Colab. So it should be pretty straightforward. Everyone should have access to it. And it should be very, very exciting. Okay. Just want to make sure my environment is properly set up before we get started. But are there any questions as of right now before we dive right in? I know Musa had one question. Hopefully that answered your question actually. So again, you did not need to be at part 1 in order to know what is going on here in part 2. All right. So today's stream should be pretty interesting actually. What we're going to be doing is training a UNet model using PyTorch for image segmentation of satellite images into water bodies and non-water bodies. So basically we're just determining, okay, what's the difference, or can we separate out water bodies from non-water bodies? And it should be pretty simple. Again, yesterday we went over some of the other use cases of image segmentation, how it can actually be used in the real world. Again, this is another example of, okay, where are water bodies, where aren't water bodies? So it should be pretty fun. We're just going to be working with some data. It might take a little bit of time to actually train the model because we are going to be using a pretty heavy data set. But again, if you don't want to use that data set, or you want to use your own data set, you can also trim the data set. You are more than welcome to do so. All right. So I did actually start pre-training a different version of the model as well, just so that we have that ready to go when we are diving into this, because again, we want to make sure that we have something to look at and we aren't just blindly accepting that, hey, this should work. We want to actually make sure it does work. So I did have another model that was trained earlier. I think it's actually still training. It's around like 97% of the way done. So hopefully it is done by the time we are finished. And then we can actually see some data and some stats about it. So we'll be seeing sort of the training and validation, as well as like we're going to be testing the model, seeing some of the images, the masks that we overlay on top of them, and the predictions for our for where everything is at. Okay. So again, it should be pretty interesting. We also can, if you want to, you can also save the model, but we won't be going into that in too much detail. That's going to be something at the very end if we do have the time for it. Okay, so what I want everyone to do is first of all, open up a brand new Colab notebook. So just go to Google, colab.research.google.com and open up a brand new notebook, and that is where we will be starting from. So let me share my screen so y'all can also see what's going on. And for anyone who wants the Colab link, that is right over here. Okay, so we are starting fresh with a brand new Colab notebook. I'm just going to name it water, I don't know, segmentation, because that is loosely what we're going to be working on. All right, so this will be, again, using PyTorch. Now, the first thing we obviously want to do is import all of our libraries. So again, just as some background for those who may not have been here earlier, I do want to let you all know that we did quickly touch on sort of how masks work and how the sort of data set that you were usually using for any sort of image segmentation kind of looks like. And we actually created that as well. If you want to, you can also go back and watch that stream after this one if you haven't already. But for today, we're going to be using a pre-made data set that is already available on Kaggle, so that we don't have to go through the entire process of, okay, we need to, create our own data set and then create the masks for the data set and then label the data set, because that'll be a lot more work than we will want to do. All right, so for library imports, we can import Torch, which is probably the most important because we will be using PyTorch from Torch. import NN from torch.nn. We want to import functional as f. That works, yes. And then from, we shouldn't be needing any of this. Functional is f, yes. Import numpy. Pi as np. Import matplotlib plot as plt. Import os. Import cv2. Import tq. Import, can't spell import, implementations as a, and then from tqdm import tqdm from sklearn learn dot model selection for test train split. Do not need this. We shouldn't be needing the data just yet. And then we want to make sure that we are actually running this on the GPU. All right, so again, this was all just importing a bunch of libraries. That is all we are doing here. Let's make sure everything is able to run. We can see if we have anything left that we might need to install that PyTorch does not have already. So I'll just leave that up for a bit and make sure that everyone is able to get that working. Let's see if there are any other comments. Hello, hello. All right. So we got that working. Again, we do want to actually make sure that we are connecting to a GPU. So if you go here, there's multiple ways of doing this, but I usually just hit this drop-down arrow and then change runtime type. And then from there, you can click on T4 GPU so that you're using a T4 GPU. It will terminate the current session. That is totally okay. But we want to disconnect and delete this runtime and then actually use the T4 GPU so that we are not running this or training any of this on a CPU, because that would take forever. Okay, so hopefully everyone was able to finish all these imports. And again, I will be uploading all of these, all this code to GitHub as well. So if you are not able to catch up, or you just you want to watch and maybe not code along right now, you can always get all of this code from GitHub later on. Okay, it looks like we have some people that are finishing up. That is good. So let's move on to the next part. We're just going to be setting a seed now to make this reproducible. So we can actually just set the seed to anything. Let's make it, I don't know, 42. That's a very common one. And then set seed, and then we want to use torch manual seed backend. Could make it deterministic and then benchmark to false. And then we can also add this random seed here. And then we just want to actually set the seed value. Ooh, set underscore seed torch dot manual seed. Did this not import torch? Okay, I need to rerun everything because I changed my runtime type from a CPU to a GPU. So we'll just run all the imports again. and then we should have this run properly. And then we can see that it was able to run. So that is great. Can I make the text a little bigger? Absolutely. Let me figure out how to do that. View comments, no. Hide code, no. Probably in settings, yes. Editor, font size, let's increase this way up to like 36. Whoa, that is way too big. Okay. Let's roll that back a bit. Maybe closer to 28. Okay, that's better. All right. Is that better for text size? Just want to make sure that everyone's able to read that. That is very important. I can also hide myself in a corner so that it's bigger on your screen as well. Hmm. There's too much going on in this background. Let me try and figure out how I can make this larger. Exit full screen. This background is what the issue is. Give me 1 second. I'm just trying to make this easier for everyone to see. Okay, that was not it. Huh, strange. I guess there's no way of making the screen, the actual screen bigger. What if I just hide myself completely? But I want to do it on the other side. Wow, this is unfortunate. Okay, I think I'll just disappear for a little bit, and if anyone wants to see me, just let me know. But all right, we can keep moving then. So we have our seed set, and this is basically set for reproducibility, right? We want to make sure that we can actually reproduce whatever we end up making. So that's why we're setting all the torch backends to be deterministic and setting a random hard set seed. And next up, what we want to do is actually load the data set, right? So for loading the data set, we are going to be using a bunch of images that are already pre-existing on Kaggle. We're not going to be generating anything ourselves this time around, right? So for the purposes of training this specific model, right, what we want to do is load the image and then mask it using OpenCV, which is why we imported OpenCV earlier. Then we're just going to be converting that image into an RGB format and then set the mask to a grayscale, right? And then we're just going to divide each of the values by 255. Normally they're out to 255, but we want it to be between 0 and 1 to actually apply this augmentation, right? And once it's applied, then we'll actually convert that to a PyTorch sensor, and then we will do a little bit of squeeze and unsqueeze functions in order to sort of clean up our data set and really prepare it for what we're using it for. So I know I said a lot of words. We are going to be actually coding it up, so it should be pretty simple. It's not too difficult to see what we're going to be working on. So first, we'll actually work on this dataset class. Then we can actually download the code and upload that. So we will see that happen in real time. So let's make the class for the dataset. And this class is going to be torch dot util so data set, that is good. And then init self images images, and then we have the image folder, and then we have the mask folder, and then set transform. We can set the default to none, but we will be doing some transformations on the images that we are uploading, just so that we have like more almost randomness in these images, right? Because we don't want all the images to look the same. We want to add a little bit of difference, maybe flip some, maybe rotate some. We'll do all kinds of sort of, just randomized changes or edits to the images so that we're not giving it some pure data. If like it gets an upside down image, it should still be able to separate the land from the water. So in this self.images, it's images, self.image folder, and then mask folder and transform. So this is something how your init should look. Then we can length of images, perfect. And then we have our get item, self and IDX. And over here, we are getting the image path, which is OS path join from the image folder, and we're getting all the images. And then the mask path is going to be os.path.join, self mask folder, and images. So this is basically the path to the images and the path to the masks, masked images. And that's essentially what we're doing right now, nothing too fancy. And then over here, we just want to image equals cv2 dot read image path. So we just want to make sure it's reading all the image paths, and then strip the color to RGB, and then set all that to grayscale. Okay, perfect. Okay, so all this is doing is setting the images to RGB and setting the masks to grayscale. Okay. Next, we said we wanted to divide everything by 255 so that we get a decimal value for it that's between 0 and 1. So perfect. Image dot as type a float 32, 255, 255. So this is perfect. This is basically changing all the image or all the values to be between 0 and 1. Then we want to do if self dot transform. Then we want to actually augment everything. So augmented is self.transform, image and mask. And then we are basically just setting transformed images and masks over here. And then we just want to set a return. We can do this on the sun, return. And then torch from numpy image dot permute (201), and then from numpy mask. Okay, perfect. And we can actually unsqueeze 0. Okay, so this is something like what your code should be looking like. All right. And essentially what's going on over here is if it's an image, then we apply some sort of permutation, right? After converting the change. And then we just do some sort of augmentation on it. So from height width channels, we're basically setting it to channel height width. And then PyTorch actually is going to use that, right? And then for the mask, we're adding another dimension in the front for the channel using the unsqueeze. Okay. And that's because it only has height and width. It doesn't have any channel dimensions or any color dimensions, right? So that is what is going on over here. And again, as always, if you do have any questions, please do let me know in the chat. But basically the data split that we want to use over here is 0.8 for training, about 0.1 for validation and 0.1 for testing. So we will be using the test train split function for that later on. But first, we actually need our data, right? So where are we going to get our data from? You might be asking. Well, there is this link right here, and you may need to log in. There we go. So you may need to log in, but you should be able to download these satellite images of water bodies. And let me just bring that over here. So this is the data set that we're going to be using. A little bit of context about this data set is given over here. It's a collection of water body images captured by the Sentinel-2 satellite, right? And then each image also comes with a black and white mask, which is what we're using here, where white represents water and black represents something else that is not water, right? Could be a building or a ship, I think, as you can see in this image right here, or it could be land. So these were actually all calculated masks, but it should still be pretty good for our use case. All you want to do is click this download button over here, and then it'll give you some information. You may or may need to sign in if you do click the download dataset as zip, but that is what we are going to be doing. We're going to be downloading the dataset as a zip file, and then once that gets downloaded, we just want to upload that to our Colab instance. So mine's named archive1. I'll just rename that later on, but I'm just going to be uploading that, and we want to wait for this thing to finish uploading. Again, this might take a little bit of time, but while we wait for that, we can actually just write the code to unzip the file. Unzip q, and it's going to be archive content slash archive. Let's just rename this to archive.zip so it doesn't give us any problems. But let's do that after this thing's finished uploading so we're not dealing with a whole lot of other issues that might stem from. Let's do a.zip, why not? So we're not dealing with a whole bunch of issues that might stem from changing the file name while all the data is uploading. So once that is done, which is right now, we can just rename that to a.zip because why not? And give it a second to actually confirm, and then let's try running that. And that should unzip all the contents of a.zip in my case. In your case, it might be archive. And then if you hit refresh over here, you'll see this new folder called water bodies dataset. And this should have all the images and masks in them. And again, there's going to be a lot of images and a lot of masks. So if you do want to, you can actually delete some of these. Make sure you do delete the corresponding masks as well. So let's say you want to delete everything after 1000, you could definitely do that. Just make sure to copy that for the masks as well. All right. So I won't be doing that just because I want everyone to get the full experience of, okay, how long it'll actually take to train everything. But it would definitely be useful if you do want to see this thing finish training in less than 30 or so minutes to delete a few. So now that we have everything unzipped, actually, let me give it a second, make sure everyone's caught up and is able to unzip all of the contents of their file before moving on. That way we're not leaving anyone behind. And while we wait, we can play a little bit of background music. Okay, great. We have some people following along. That is awesome. Streamlab beats. I'm not sure what that is, but these are already on here. Some default beats going on. And I'll just wait for confirmation from maybe one more person before we move on to our next part. Or give it a couple minutes. Okay. moving on. Next, we just want to actually get our data set loaded up, right? So we can actually do it for the base path, or the directory where we're actually going to have all of our data is going to not be content/a, it is going to be content/water bodies dataset dataset. Okay, that is correctly spelled. And then we want to make sure that is a folder. Image folder is going to be images with a, I believe it is a capital I. Yes, so we can change this to capital I images, capital M masks. And then we want to list the directory over here. Then we actually want to do our test and training split, right? So for our train images, we will have, let's do train images, test images is going to be the test train split of images with our test size of 0.2 and our random state set to 42 because that's what we said earlier. And then we want to also have our test images and our validation images. Test images and validation images to a test train split with a size of 0.5 and a random state of 42. So you can just use whatever default this already gave us. And let's actually run that to split everything into the test train. And we can see that that runs perfectly fine. Now, to actually set our data set sizes, let's say we wanted to visualize what our data set sizes look like. So in that case, we can go with data set sizes and make a quick just bar chart of length of, what is this, that train images, length of validation images, and test images, and then set the labels to train, valid, test. And then we just want to make a quick bar chart. So plt dot bar with labels and dataset sizes. And this just gave us a whole lot of other information, which is great. And if we run that, we can see that this is sort of what our dataset size looks like, right? So we have around over 2,000, maybe 2,500 almost, just training images. Then we have around 250 for our validation and 250 for our test. Okay, so we're going to be training our data set on a random sampling. We're using 42 as a seed of about 2,300 training images. Then we have validation and tests over here. All right. Hopefully everyone is following along. Okay, I'm not seeing any complaints, so that is good. And do let me know if I'm going too fast. I will definitely slow down. But this is what we have for our data set. And most of it, thankfully, Gemini is now built into Jupyter Notebooks, so we don't even need to have to type up everything manually. It is super useful to just let Gemini do a lot of this stuff for us. Okay, next up, we want to actually do all the sort of image transformations on our training, validation, and testing data sets. So let's do that really quickly. So if we did train transform equals A, and A is what we're using for our image augmentation. You might remember that we actually imported that earlier. Dot compose we can first start with resizing. So A dot resize 256. 256, yes, that looks good. And we're going to get to that later. Hopefully we can just get AI to do more of that for us. But next up, what we want to do is also maybe put in around half of them to flip horizontally. And then we can also have a few of them flipped vertically as well. A dot vertical flip. And we can also do a random number of rotations. So a dot, I think that says random rotate. This is random brightness contrast. Let's just do random rotate of between 90 degrees and P equals 0.5. And that looks pretty good. Okay, so that should basically, sort of jumble up some of our training data so that it gets resized like this. And honestly, we can just copy and paste everything that we just put earlier. And we can do the same exact thing for, oops, I did not copy that. We can do the same thing for our other data sets. Control C, I keep hitting save. So for our validation, we can also transform. So val transform equals, and then just paste this. So it'll be the almost exact same thing, right, with the random rotations and everything. Then for our tests, we actually don't want to do all of that, right? Because we are testing how well our model works on the given data, regardless of what the training or validation data looks like. So for test transform, we only want to resize everything to be this, this fixed image size, and we're not going to be doing any fancy flips for that. All right. So next we want to just set the train set, the test set, and the validation set. So train set to the data set of training images in the image folder, mask folder, and transform equals train transform. So we can honestly just use all of this to autocomplete. Same thing with the validation and tests. And then we can set the batch sizes for each. So let's do that. Train batch. Let me scroll down a little bit because we don't have any code up there. Train batch size to not 16. We are setting this to 32. Same thing here. And then the test batch size, we can honestly just set to 8 because it is not a huge set. Then we can honestly just run the train loader, which is going to be the torch.utils.data.data loader. And we are basically setting a bunch of info for here. Train set, batch size to train batch size. We do need to add the number of workers. So we can just slide that in right here. Num workers equal to 2. And then shuffle workers. And we can honestly just copy paste the num workers to, whoops, here. Shuffle to false, that's for validation, and same exact thing for test. Num workers to 2, batch size, and okay. And hopefully that should get us all of our, okay, data set is not defined. Interesting. Data set. We have our data set set over here. This class, oh, was that not run at all? Interesting. Okay, I think I just forgot to run the class with the data set, but we can run all of this again. And then we should get this thing to work. Okay, perfect. There we go. So this all seems like it is working as expected. Okay, any questions about this so far? I am going a little fast. So we did get a question. Is there a reason that we only transform the images? Let me move this. There we go. Only transform the images after we have done with the train val test split. Usually the only reason for that is that we want to make sure the test still stays the same, right? As you can see, we're not doing a whole lot. We're not doing any major changes to the test data set. We're not doing any horizontal flips, any vertical flips, because we want the test data set to be as pure as possible basically exactly what we get from any data set that we might get anyways, right? So the data set that we are currently getting is from real data. So it is from like this, basically the satellite images that were collected here. That is the data that we're getting. We want to make sure that that data is that, which is the pure data, is what we're testing on to make sure that that is like as clean as possible, right? But for training and validation, we just want to jumble up the data a little bit. We don't know what angle we might be getting this training data from, so we want to essentially randomize or add another layer of randomness to the training data in case we get some very stale or very what's the word for this? Yeah, so essentially if we get some very stale data, right, some very uninteresting data where everything is very well lined up, we want to sort of add a little bit more info here, right? So resizing it, flipping it around, vertical flips. And this is generally good practice for any computer vision task as well, right? So if you're, for example, we gave an example earlier in part 1 about the medical imagery, right? So for medical imaging, normally you might have a picture of a scissors or a picture of like a scalpel. But if you only took pictures of that scalpel from one specific angle, you wouldn't be able to, really get every single one of the angles that it might show up in an actual computer vision application. So you want to add like more flips, you want to add some resizing to make sure you are covering for as much of that as possible. There is also, again, potential occlusion and other things that might happen with it, but we're not going to worry about that too much right now. So hopefully that answered your question. We did get a follow-up question too. Isn't the validation set also used to validate the ability of the model to generalize real-world images? So why do we do these flips on the validation set? So the flips on the validation set are just to make sure that our training is also good, and it's really just to make sure that we want to validate on something that is similar to the training, then the actual test, like the real test of what we're going to be doing, is real world data. So it is, again, optional if you wanted to do it on the validation set, but it's good to compare as well between the training, the validation, and the test, right? You want to make sure, you want to see, hey, this is what the validation output looked like, and this is what the test output looked like, and they are different maybe for some reason. Why are they different? And then you'd know that this is the reason, versus if you did validation and test being the same, you wouldn't be able to do that. But that is a great question. And hopefully that answered it. If it didn't, please do let me know. I will do my best to clarify further. Awesome questions. Okay. So hopefully everyone was able to get at least this much done, right? With the help of Gemini, it is generally a little bit easier. Awesome. Glad that was able to clarify. And next up, we actually want to design the UNet model. And now this is going to be a lot of, I wouldn't say a lot of code, but it is going to be, a custom model that we are writing up. So I'm going to go through this a little bit fast just because this is the convolutional neural network that we're going to be using for training. And normally you wouldn't necessarily always be, writing your own network architecture. You could always just import one, but we'll be writing one just because why not, right? We can always see what's going on behind the scenes. So double conv, let's get right into it with our module init a self in channels and out channels, and we have self super dot init, and then we can get right into it. So self dot convolutional neural network, CONV is going to be a sequential neural network of n dot conv 2D with in channels, out channels, and a kernel size of 3, padding of 1. Then we have batch norm 2D with out channels. That's good. Then our ReLU, and then our double conv 2D out Whoops, this is in channels, then out channels. Same thing, batch norm 2D with out channels, and then reloop. Okay, perfect. And then we have our forward, which is self x, self.conv x. Okay, perfect. So this is basically going to be our network that we're using. Again, super simple network. And we can also have a downstream class down, and then an n.module. So when we're initializing it to in channels and out channels, init self.down. Oops, self. Sequential. And this should be relatively easier with just a max pool 2D of 2 and double con with in and out channels. And then another forward pass. Okay. And again, all we're doing here is basically having a pretty simple network. We're just creating our own sort of custom network architecture. This is really just what works best from my experience, and I've also looked at a few research papers, but you can experiment and change some of these around as well if you want to. Try other sort of other functions and see what works best. All right, next we'll have an up with module in and out channels. And let's also have a bilinear, false by default. And then we just want to change this based on whether it is bilinear or not. So if bilinear up is, oops, sequential, and then the upsample scale factor of 2, bilinear mode, align the corners, and then conv2d with in, out, and a kernel size of 1. But we want to change the out channels because it is bilinear to half. Okay, there we go. Else. And then self.up is transpose 2D in out over 2, 2, and stride equals 2. Okay, perfect. And then we want to just set the double conv in channels and out channels. Okay, perfect. So this is what we have for our up. Let's also create a forward with our x1 and x2. So x1 is self.up x1, and then we have the diff of x and y. So we have y is x2 size 2 minus 2, 3 minus 3. Okay, this looks good. F.pad x1. Make sure this is correct. Diff x over 2 x is x over 2y minus y. I think it should be over 2. Okay, perfect. And then torch.cat x2, x1, dimensions of 1, and return this. Okay, so this is just a forward feed function. Don't worry about it too much. You know, it looks really complicated, but I promise it is not. This is basically just using the functional module from the torch neural network to really just pad all the images, give it some padding around it to make sure that it's not just looking at, you know, it's not looking at some borders or anything of that sort. So don't worry about all of that. Make sure there's no questions. Okay, I think everyone's just trying to follow along real quick. Anyone need me to go back anywhere? Do let me know. Okay, looks like everyone is good. I love that. Okay, then we can work on our very last class, which is just going to be the outconf. So for that, it's going to be class. Okay, gave us basically most of it. Should just be pretty simple. Self in channels and out channels. The super, and there we go. And then we have the conv dot 2D with in, out, and a kernel size of 1. That looks good. Then we want to also set a sigmoid function. So self.sigmoid, and then we have our forward with self and x. All we want from here is conv and sigmoid, then return x. Okay, so this is, again, all we need for our out convolutional neural network. Let's try running that, and that looks like it ran successfully. Okay, great. So again, this was just really a very quick exercise in getting some neural networks, right? Again, you can change these around if you want to see what works better for you, but this is really just, according to some research papers, some of the best architecture essentially to use when trying to work with images, especially masked images. So that is why we are using it. Okay, next let's actually work on our UNet class. And this is going to be, honestly, there we go, kind of, I wouldn't say boring or annoying, but hopefully Gemini should be able to complete most of it, right? So let's get self.inc is the double convolutional neural network with n channels and 64 bits, down 1 to 64, 128, and 128, 256. So again, this is basically just actually running that whole UNet model that we just defined earlier. We have down 3, we can upscale it to 512, and then 512 to 1024. And then we can do our upscaling then. So we set that downstream, then upstream from 1024 down to 512, 512 to 256, 256 to 128, and then we can set it from 128 to 64, and then our out is going to be 64 with n classes. And then for our forward, we have x down 1, down 2, down 3, and then added down 4, up 1, up 2, x4, x3. Okay, started messing up. So x3, x3, x2, x2, x1, and then x for our logits. Okay, and then we just want to return logits. There we go. So again, this is just our forward network going through this, right? We're essentially using everything we created earlier, right? And then just going down the function, then up the function, basically upscaling and downscaling the image and running it through the algorithm in order to running it through these machine learning algorithms or functions to get the optimal, results. Okay, and let's try running that. Hopefully that works as expected. Perfect, no errors. Yet we haven't called anything. Okay. So that was our UNet model. And it is currently 6:56. I do want to give you all a break as well before we keep moving. So let's take a 4-minute break. 4 minutes, 6:56 where I'm at. So just top of the hour, wherever you are. I guess there's only 3 minutes left now. then we can reconvene. Actually, let me answer a few questions. Let's just see, we got one in the chat. Am I using Safari or Chrome? Can't even upload the dataset to the session. Just has a red circle. When you drag it over and press upload, nothing happens. Are you uploading a zip file or just the unzipped folder? You do need to upload a zip file in order for it to upload properly. And also, before you do so, make sure you're connected to a T4 GPU so that you're not working with CPU runtime. And then when you change your runtime, then everything gets wiped out. So make sure you upload your zip file first, and then you wait for it to finish uploading before actually trying to unzip it. If you try unzipping it before it's done uploading, it will just break the file that gets uploaded, and then you'll get an error, and I think it'll like assume that it's a zip bomb or something, and then it won't unzip it. So then you'll have to start that process all over again. So upload your zip file. Wait for that to finish completely uploading over here, and then you can run this unzip command. Someone else asked, how do you choose a kernel size? Kernel size where specifically? In the convolutional neural network layer. Over here, really, this is based off of the images that we got in the data set. So if you actually go into the data set and take a look at sort of the info, we'll find that this specific kernel size is optimal for our use case right now. So it's really just width and height of the filter mask. Normally, you'd want to use sort of multiples of 8 because that is how many bits are in a byte, and that is how most information is stored. So you almost always would end up using sort of multiples of 8 in this case. Said, okay, so you're just trying an unzip folder. It should be loading now. That is awesome. All right. Well, I will leave this up. Let's take 5 minutes and grab some water, and then reconvene in 5 minutes. All right. I will see you all in 5 minutes. And until then, enjoy some music. All right, we are back. Let's pause this. Okay. So, I guess that works. Let's see. We left off with finishing up our UNet class, and this was basically the network that we're going to be using for our network. All right. And let's see. Okay, so we did get a question earlier about how do you choose the kernel size. I completely misunderstood the question. The kernel size is actually usually you want to keep it as low as possible. Generally, the most commonly used kernel sizes are 3 by 3 or 5 by 5. And the kernel size is really just to sort of reduce the number of similarities essentially that you have between maybe multiple classes that you're trying to have this model determine the similarities between, right? So the fewer basically classes you have, the more likely the model is able to pick up on relationships and similarities versus if you had a much larger number of kernels, it is significantly more difficult to find the difference. So in this case, because we're just using black and white, a kernel size of 1, just images themselves, kernel size of 1 in this case is okay. For two-dimensional, kernel size of 2, right? So et cetera, et cetera. You basically want to keep a lower kernel size to reduce the number of classes that are being looked at by the model at one time. Hopefully that made sense, or at least a lot more sense than the previous answer that I gave. All right, moving on. So we finished up with writing all of this, and we were able to get hopefully our folders unzipped. Now we are going to move forward to our dice function. So the dice is basically just going to be the loss function that we're using. And the loss function, we're just going to be taking the sum of a BCE and dice loss. So the dice loss is basically a coefficient that's calculated using a specific formula of 2 times the overlap area divided by the total area. So that should be pretty straightforward to actually implement in our code. So let's do that next. So we can honestly just type in the dice BCE, new class, dice loss. Let's do dice BCE loss init with self and smoothness. Okay, and then let's see what our forward looks like. Self y. No, we are doing logits for this and targets. And then we're trying to find the intersection, which again was 2 times logits times target. Okay, so logits times target, get the sum of that as the intersection. We need, this is not correct, hold on. Let's do 2 times dot sum plus the smoothness, and then get the union of logits plus targets and smooth, and the dice loss, again, like we mentioned earlier, is 1 minus the intersection divided by the union. Do not need this. And we're just going to write 1.0 so that we get decimal values. Okay. Then our BCE loss is going to be loss equals, and we can just use the existing E loss. And then we just want to return the dice loss plus the BCE loss. Okay. Then we want our dice coefficient. Let's see if this is correct. It's target intersection at 2 times logis plus or times target, get the sum of that. And no smoothing over here. Union is going to be logis and targets, no smoothing. And the dice loss is going to be this. We do not need this. If union is 0, we return a 1. Otherwise, we return the intersection divided by the union. Oops. Okay. And this is just basically getting our loss function right here. All right. So nothing too complicated going on over here. It's, again, just a pretty straightforward loss function. See if we have any questions in the chat right now. Okay, looks like we are good. Next up, we want to actually define our training function. And this part is going to be the one that probably takes the longest to actually run. But we're going to use a low number of epochs so that we are not spending all day here. So let's start with 10. Normally, I think 30 is a pretty good number so that you can get to a more stable or consistent result. But for the sake of time, let's use the number 10. So for our loss function, we're using dice BCE loss. For our model, we're using unit with 3 channels and 1 class. And we can honestly, we can send it to the device. So we're sending it to our GPU so that's what it is running on. So we're not sitting here running it on a CPU instead. And then we have our optimizer set to Atom. Again, it gives good accuracy. It's pretty fast. So we'll just use that and set the model parameters and our learning rate to 0.001. And let's actually set the train losses. Train losses, the train dices, so that we can actually store all that info and get access to it. Val losses and val dices set to train, and the model, the train loader, the optimizer, the loss and number of epochs. Okay, and this should be what trains our model. Do we not have a train function set? Okay, let's try running this. And then this should hopefully start training. The train is not defined. Let's see what's up with that. Did we write our train function yet? We did not. Okay, let's start with our train function. That'll do it. So this is going to be a slightly longer one, and we just can use all the inputs from here. So for our actual train, we set in model train loader optimize loss and epochs. We can set a default as well to 10. If we didn't actually set one, train losses, val losses, and dices all set to empty. And then for each epoch in the range, let's do in TQDM. TQDM range epochs. We are actually model.train. And then set our train loss and dice to 0. Now for images masks in the train loader, we have images and masks to device. Then we have our optimizer with 0 grad, and then we just need to set everything else. So logits equals the image model, L is the loss value with logits and mass. Then we want to step backward, optimizer.step, and then the train loss we want to actually increment with the loss value, and then the train dice we want to increment with the dice coefficient. Train loss equal to, okay, yeah, we're setting the loss to fraction of the train loader, and then doing the same thing with the dice, and then we want to train losses append, and then train dices append. Okay, so this is basically just getting all of that information and storing it for us in this so that we can actually take a look at it later on. All right, and then we just want to do some actual validation. So let's move on to that. So evaluate the model. We have our validation loss and validation dice set to 0 with torch no grad. We can iterate again. This is going to be very similar to the previous code that we just wrote. Loss value, increment everything, append everything, and then we can have a print statement. So current epoch divided by the current number. We do not need all this. Okay. And then the train loss, and then the train dice coefficient, and then the validation loss and all the other information that we might want. And then from this, we obviously want to return train losses, train dices, val dices, and val dices. Okay, so this should be our training model again. And once we run this, it should start running successfully, and you can see it did not. See what the error is here. Groups 1, weight of size 6433. Expected an output over here to have 3 channels, but got 64 instead. Okay, where did I mess up? The train losses. Let's check the full stack trace. See if there's any questions before I do that. Okay, looks like everyone's good. 500, 1000 container module. Over here in forward self X, Python input, train losses, logits to model, images, And then in the model itself, it's being called how. In train, oh, this is 16, and forward. Convolution. Okay, there's some issue, I think, up here. Kernel size of 3, padding 1. Interesting. And again, if you all have any recommendations on what might be wrong, do let me know. I would like to get this solved as quickly as possible. This would be a good time to run that music. You can watch me debug. Okay. Forward. Here, x1 to x5 should be correct. See an issue here. And then 5, 4, 3, 2, 1, all the way down. Set to out C. Okay. 64 to N, 128 to 64, and we do the same thing down from up here. So the unit is correct. I think there's an issue with the network itself over here. In channels and out channels, 3 padding 1. Batch norm the out channels, ReLU in place, column 2D. That'll do it. Out channels over here for the second pass. And then batch norm and ReLU with out channels. Okay, let's see if that fixes it. Rerunning this. Please work. Did not work. Okay. Looks like that is along the right lines. Expected output of this got way more channels than expected. Or no, way fewer channels than expected. Okay, let's figure that out. I think it's still an issue with D. Well, let's take a look at the stack trace again. Any issues are in con.py. Convolutional neural. No. Okay. Run on up. First time when it's sending X5 upstream. Okay. Let's go back to here. And figure out from here what's going on. We are double out, in place, forward. Should be right. Bilinear, the scale factor is 2 and we're upsampling it. You can see this is an issue with using AI to write all of your code. Sequential upsampling with a scale factor of 2 in bilinear mode, corners aligned, and then you through a convolutional neural. 2D with in channels, that'll do it again. Okay, kernel size of 1. Alright, I see where I messed up there. And then conv transpose 2D is also in channels and in channels, then the double conv is in and out channels. Okay, that looks significantly more correct. Let's double check everything else with our outconv function where in and out channels exist with a kernel size of 1. Then we run it through a sigmoid function. Okay. This should hopefully work. Let's see if that fixes any other issues that we might have had. Moment of truth right here. And that also did not work. Oh great, CUDA is out of memory. Okay. Cool. That means we likely... How's it out of memory? The RAM spiked up. But I do not... Oh, that's probably because I'm running everything else. Let's let it cool off a bit over here. And then, if that does not work, then we will have to disconnect and then reconnect again. But that hopefully should have solved our issues. Let's actually try running it one more time. Yeah, I out of memory again. Like no free memory right now, which is interesting. Don't know why that is the case. Let's try reconnecting. That does mean we would need to re-upload our file, the zip file, but shouldn't be a huge issue. And again, if you didn't catch the changes, that was just some issues with the network. Okay, it looks like it has all this data, which is good. GPU RAM is at a complete maximum though, which I have no idea why that's the case. It should not be that high. We'd have to change the runtime type to, let's say, a CPU. Save this. It's going to reconnect, and then we'd have to, again, re-upload everything. And then rerun everything as well. But hopefully it gets working then. Okay. And then connect to a hosted runtime. Change to a T4. Yes. Save. Cannot connect. Due to usage limits. Okay. Looks like I maxed out another GPU and they were not happy about that. So I'm going to try running this using a CPU. I do not recommend anybody else do that. Please run it on using the GPU, otherwise it'll take a while for you to finish the training. So we're just gonna wait for this thing to finish making a round around the Earth, but in the meantime we can try all of our imports. And you can see it's going to take significantly longer because we do not have a GPU to speed things up. I was trying to use RunPod earlier, and if you don't know what RunPod is, it's essentially a sort of cloud GPU platform. I was actually trying to use that, but it gave me a ton of import errors, specifically with augmentations, which was unfortunate. I think it would have been really cool to be able to use that. And honestly, if we do have extra time, we could actually try that out. So let's just wait for this thing to finish uploading, and then we can try unzipping it. Archive.zip, there we go. And then that should finish unzipping into the water bodies dataset. There we go. Reading all the images, figuring out the test train validation sets, actually running all of our classes, basically loading those up. And then we want to figure out the train. And now this right here is once again the moment of truth. Now this will probably take a long time, given that I am running this on a CPU and not a GPU, but it looks like it has not aired out yet. It might just be because it's very slow. But if you all are also following along, hopefully it is working on your end now. Yeah, this is going to take a while. You can see the system RAM is climbing up like it's nothing. So let's see where this goes. 7.5 gigs. This is very interesting. .2, yeah, this is just climbing up and still at 0%. It should update after every epoch. Let's see if it at least runs one, and then we can try something else. But do let me know if you were able to get this working, or you do have any other questions about any of this while we wait for this thing to run. Okay, it looks like it peaked at around 11 or so, and now it's dropping a little bit, which is a good sign. That means stuff is going on. You can see there's some, okay, it's running the backward right now in training, so it's going through all of that. Looks like it is somewhere. Where's train? Okay, it is going through the backward step right now, somewhere around here. And it has been 2 minutes and still hasn't finished a single epoch yet. So we can actually see how long this will take just by projecting the first one. Maybe I should try connecting to a GPU again. It might be faster. What do you all say? Connect to a GPU or let this thing run at least for one? All right, we are connecting to a GPU then. I do want to see this hit at least 10%. Oh, 3 minutes in and nothing has happened. Nothing interesting has happened. So let's change the runtime type and hopefully do not get banned from Google for using a ton of GPU power. Okay. Oh, still usage limits. Great. Looks like I've maxed out my usage. Start reconnecting. No, it doesn't let me. Okay, what I'm gonna do then is, oh, it won't even let me copy paste it to a different file. Let me open up a new Google account and then see if that works. Okay, looks like I'm able to open up a new one. I'm just gonna copy paste all the info over. So that should be pretty quick. Random seed, and then add another code. The data set load, and then more code. This is going to be the unzip. More code. Here, copy this over. You can see how many issues come up when trying to use a GPU. Okay, more code. Copy. Paste. Copy. Paste. I just realized I probably could have shared this notebook with this other email account and ran it on there, and it should have done the same thing, or it should have actually done it properly, but too late now. Okay, so now this is what we are working with. Let's open this up, connect to a T4, hosted runtime, whoops, change runtime type to a T4 GPU, yes, save, and let's go. It is connecting me to a T4. Beautiful. Now I just need to upload this archive.zip file. Okay. And wait for that to finish uploading. And once that is done, or we can also start running all of these while we're waiting on that. So it's going through the imports. It was able to import everything. We got the seed set and the dataset class. Now we're just waiting on this to finish uploading before we can unzip the contents of our folder. Then we should be able to get to everything else. Okay, let's turn the music off. Things are starting to heat up. They're really not. We're waiting on a loading sign. Okay, let's see the usage stats as well. That way we can make sure we're hopefully not absolutely maxing out our RAM in our GPU. Okay, so it looks like this is ready to go. We can run this. And that should have unzipped everything. Okay, perfect, into our weather data set. Run that, run that, run that. And this looks correct in terms of our training and validation. We can run this. Our GPU RAM is still at 0. That is what we are looking for. Still 0. So a little more system RAM. And okay, this is the moment of truth. Hopefully this works now. Fingers crossed. And we're probably going to be seeing a big spike in our GPU RAM. You can see that this is actually executing significantly faster now on a GPU. Yep, a GPU spiked up to full usage immediately, which is fun to watch. And we just need to wait for this to run. Okay, good. It's stabilized a bit, so looks like this is executing as expected. It is just trying to train this entire model, which shouldn't take or it might take a while because we're giving it 10 epochs, but it should hopefully run successfully. Now, honestly, while we wait, we can write everything that we need for actually visualizing it as well, right? So we want to actually see what we're doing with this data, correct? So let's actually get right into that while we wait for this thing to finish running. So for that, we're just going to be writing a bunch of like plots, right? So PLT, oops, PLT dot figure big size. I don't think I have any autocomplete enabled on here. 210, 6. Okay, and then plot of 1, 2, 1 set PLT dot plot, and we want to actually plot the epochs as the x value. So arrange the epochs and train dices. And then plt.plot and p.arrange epochs again, and this time it's the validation dices. Then we can just clean up our actual, whoa, did this only, what do you mean only ran one for 1 minute? This is not what I was looking for. Is there an issue with the train loop in range? Epochs. Okay, well, we got our, I guess, an example of sort of how it would end up looking with our training and validation. Do not know why it only ran once, but the GPU is still maxed out, which is interesting. Looks like we haven't actually, there's definitely some issue in here, which it hasn't released the memory, but we can get to that later. Let's first see if we're able to plot whatever was able to get made, right? So for that, we can have the X label, or we already know that the X label is the epochs and the Y label is the dice coefficient. So let's create a subplot of 1, 2, 2 and plt.plot np arrange, and we're using numpy to arrange the box and the training losses, and then do the same thing but with the validation losses. So arrange val losses. Okay, and then we honestly don't need legends because we know what is going on. No attribute arrange. Oh, I spelled arrange wrong. That's embarrassing. Oops. There we go. So it would end up showing on here if this worked. Let's honestly try running this again. We'll end up like absolutely maxing out our GPU one more time, but probably get kicked off again. Hopefully not. Let's see what the issue might be. The learning rate looks correct. Definitely some logic error in the training. Losses, dices, epoch in TQDM range, model.train. Oh, let's not use floating point numbers here. Okay. And for eye images, masks. All right, let's try this. We can kill this, rerun this, and this should hopefully give us a slightly better result. We're going to change this to 2 because 2 is faster than 10. And now we wait. This is a great time to throw on the music again. No, this is gonna make me go to sleep. Let's go to this one. This is very MLH. Let's go. Yeah, there's a little more hype. Let's go. We all love watching models train. It's the most exciting thing in the world. But again, as always, if you do have any questions, please do let me know in the chat. That way I can do my best to answer those. We have around 15 minutes left together. Lewis, were you able to get yours working? I know you said you were, I think, still working on trying to get the folder uploaded. Do let me know, and Mitran also let me know where you're at with this while we wait for this thing to finish training. Okay, good. We have ran all of these boxes, so there should be no issue. I think we just really do need to wait. Oh, completed. That is once again not what we are looking for. Channel's correct. To device, use the optimizer. Add a model parameters. 001. Oh, is this out of the validation loop? That would do it. Okay. Great. That is... Wow. That is a horrible, horrible reason to be having any errors. But I think this is all supposed to be inside of this for loop. This for loop should end right before this. And then we have all of this happening over here inside of this for loop, this happening under the with. Okay, wow, that was embarrassing. So the issue here was that the return statement was inside of this for loop instead of the outer for loop. Or it was inside of the for loop instead of the function. So this should now work. Fingers crossed. But now you can see what all the potential errors that you might encounter when you are actually making this for yourself might be. The GPU RAM is also completely maxed out for some reason. Don't know if we can release it somehow. Ooh, okay, this is running stuff, so that is good. I'm seeing some progress. As soon as that's completed with just 2 and we know it works, then we can move on. And again, in your free time, you could always update that to 30, 50, however many you think would work best. it is best to experiment a little bit and, find out what works. Getting more Gemini ads. Okay. Okay, back to training. Back to training. Okay, there we go. We can see a 50%. So this has been the most progress we've made in this entire stream. So that's awesome. You can see that it is half the way done. The training loss right now is around 0.86. The training dice is around 0.6. Validation loss is about 0.8, and dice is around 0.6. So kind of bad again, but we are starting out right now, and we're only really doing 2 epochs, so it's not going to be the fanciest thing in the world. Okay. And once this is done, again, the first one I think took around 2 minutes. The second one I think it's around halfway done, should take about maybe 1 more minute. And then we will be done with both epochs when running this. Again, it won't be the most accurate thing in the world. Again, look at the learning rate. It is very small at around 0.001. So not hugely optimized, but we do just want to see the numbers. And I do have another pre-trained version of this that I can also go into. Okay, great. So that's done. Now let's try running this. We still get another error. I spelled arrange wrong again. Okay. There we go. So this again is just going to be looking like a straight line because we only ran it on 2. But you can see that these are almost inverted, right? With our data. And that is really what I wanted to show you all, that over here, we can see that the training dice and validation dice is going to look, it obviously is not going to look this, clean with a bunch of just a few straight lines. It's going to look a lot messier. But we can also test this model, and we are running a little bit low on time. So I am going to try and go through this testing part as quickly as possible. But for that, we just have the, let's see, images and masks. Masks to next iteration of the test loader. With torch. Sounds like I'm against the clock using this violin beat. Grad. Prediction to the model and images to device. Device CPU detach, and then set the prediction value equal pred over maybe 0.5. Display. Oh, where's the enable Gemini feature? I feel like this could actually be useful right now. Autocomplete. Display image, images, masks, and predictions. Image, ooh, do not want to. equals images.permutate 0, 2, 3, 1. And then images.numpy masks equals masks.permutate. Zero, 2, 3, 1. And then same thing with the predictions. 0, 2, 3, 1. There we go. And then images. Again, this is just to actually take a look at what we are trying to do is numpy concatenate the images on axis of 1. Masks, same thing on 1. Predictions on 1. And then we have the figure and axis plot subplot 3, 1. Figure size of 20 by 6. And then figure, whoops. Fig dot tight layout, and then show images, set title to images, sure, show masks, and then CMap. Equals gray. Set title masks, predictions, color map to gray, and then we just want to display this. Images, masks, and predictions. Okay, let's see if this runs. Hopefully it does as expected, and okay, there we go. Now this is basically what it was all for, right? All that work later. Let me turn this music off. Whoops. Pause. There we go. I got some spam in the comments. Okay. But essentially, this is what it was all for, right? So you can see that these were the masks and these were the predictions, and it did do pretty okay on some of them, right? Let me try zooming in here. If it will let me, there we go. So you can see that, like, say for this first one, right, we can see that the given mask over here and the given prediction were actually pretty close, right? Same thing for maybe the second one. This third one, we actually got a better prediction than a mask. Actually, I'm not sure if that's better. That is not better. It detected this as a body of water, even though this isn't a body of water. This is supposed to be just like nothing. I think maybe some buildings or something, but still detected it as a body of water. Everything outside of it, which is a little strange, right? So again, remember that white is supposed to be considered water, black is supposed to be considered land. There was absolutely none of that, and it's still considered that to be land, right? Over here, we have water in the middle. It was not able to detect that that was water. And again, this is only on 2 epochs. So it is actually doing really good for, only 2 really real runs. So we can actually see that if we, maybe ran it a few more times, there would have been significant improvements. But even with just this much data, we can see that there's a significantly, it is pretty accurate with whatever it is given. So that is essentially everything that it was there for, right? So we went over from part 1, the sort of masking how all this pre-processing works in order to get this specific mask that we see here in the prediction or in the given mask, right? Then you can see that we have some sort of rotations as well to try and jumble this around to see if everything looks or confuse it a little bit. That's what we did today. We just worked on actual implementation, and yeah, hopefully that was a helpful stream. Again, I am at time, but hopefully you all were able to learn something. Thank you all so much for coming. I do have a quick ask of everyone. to please go to this link right here, or is mlh.link/GHW or Global Hack Week feedback, and give feedback about the stream, whether you liked it, if you didn't, what you think about Global Hack Week in general. But again, we were able to get all these images and do exactly what we set out to do. So again, thank you all so much for being here, right? Thank you all so much for watching. If you did stay until the end and bearing with my, any mistakes that I might have made. And hopefully you all will be joining the next stream. And yeah, I'll see you all around. All right. Bye, everyone.